All right, so unit 10, our final unit, mostly advanced alignment. As we jump into this, remember this is not your typical pull a car in and do an alignment based on they got new tires or you're not going to get into this if you've replaced a rack and pinion or something. This is going to be for problem cars. So as part of problem cars, I would also like to include if you've got a car that has a pull, that's going to be one of the main things we talk about right here. Remember, a pull could be caused by tires. And so rather than lecture a lot on it, we've made that video where we had a customer who had a pull on a Kia Kona, Hyundai Kona, a Hyundai Kona, and we ended up actually doing a side-to-side rotate, right? So right off the bat, if a car has a pull, you got to decide, is it tires or is it alignment? And if you know your alignment numbers well, I would say go ahead, pull it on the alignment rack, do the compensation, take a look at what the measurements are. And if you can interpret your measurements effectively, you will know if the pull is caused by the alignment. In the case of this one, as you'll see in the video, it had alignment numbers that would actually make it pull, if anything, slightly to the left, but the customer concern was that it pulls right. And originally we just assumed we do alignment, but when you look at the alignment, don't just make it green. Understand what you're seeing. Understand if what the alignment numbers are is correlating to the customer's concern. In this case, they didn't. So we knew, hold up, wait a minute, something ain't right. It's not the alignment. And we went ahead and we did a cross rotate, meaning we pulled the left tires and wheels off and we switched them with the right, drove the car, and it now pulled hard to the left. So what changed the pull? It was pulling to the right and now it pulled to the left, rotating the tires. So at that point, we knew this pull was actually caused by tires. That's not very technical, so that's not a big lecture point. However, if it was an alignment issue, like let's say we rotated the tires and it didn't change it, and yet we were looking at our caster camber toe thinking that should pull to the left, but it's pulling to the right. There are other numbers and other measurements we could take to determine if something else is wrong. Okay, so that's kind of where we're going. And then as I pause in just a moment right here, it also reminds me to point out sometimes customers' concerns are more vibration based, and if we're dealing with a vibration, we're not likely getting into advanced alignment. You're more likely to go right back to the basic tires and do your road force balance. So in this unit, I used to cover more advanced tire material, but since then, because we've got the machine that's integrated, we really covered tire vibrations as part of tires several weeks ago. Okay, so that's your vibration and pull outside of alignment. Now let's get more technical on alignment. First, we're going to talk about the steering axis inclination. So if you were to look at the front of the car and you were to line up the steering axis, right, and a McPherson strut, we're talking about the upper strut plate, we're talking about the lower ball joint. That angle right there is the SAI, okay, steering axis inclination. Now, what's interesting is SAI is kind of viewed from the front. If you were to look at this car, if you were to flip it 90 and look at it from the side, the SAI and the caster are really closely related. Caster is kind of like the angle front to rear, and SAI is the angle side to side. They both have to do with the steering axis. So if we're worried about the steering axis, you can't see that. I mean, you could pop the tire off and you could take a look, but you don't have a real good way to measure that. There are some symptoms, but realistically, the way we're going to find the SAI is we actually need to go in the alignment machine and tell it we want to measure SAI. A lot of times that's a setting they'll call it like SAI with faster caster, and it's pretty much the same procedure as measuring caster, but you have to request it. It won't just automatically give you your SAI numbers. Okay, then everything I said is the same. If we've got a double wishbone, we're looking at the lower ball joint and the upper ball joint, right? Because again, that's where the steering pivot is. That's the steering axis. And we're going to constantly compare the steering axis to the true vertical line. Now, that's kind of weird. Like right now, it looks like we're comparing it to the tire, but actually, that's not, we're not really trying to compare it to the tire. This would be true vertical, which would mean plumb bob. You get a string with the weight, you hang it from the ceiling, it will automatically find true vertical line. We'd call that like plumb, the word, not like PLUM, PLUMB. Okay, that's where we pull the caster number from. The actual tire, if that's at an angle, that's actually camber. Okay, so it gets a little bit weird. SAI is a little hard to understand because you've got true vertical, plumb, you've got camber, which is actually how the tire's sitting, and then you've got SAI, which is the steering axis. And then we're going to add another more complicated one there called included angle. This is the reason I don't cover this as part of alignment. Alignment, I want you to learn caster, camber, toe, a little bit about thrust angle. We don't need to make it very complex. All right, so continue. When we talk about SAI, the reason we have SAI is it develops what we call a spindle arc. So I'm gonna essentially show you what spindle arc is. If you were to have an old school car with a spindle and your wheel bearings are here, when you turn, it goes like this. It's kind of like some sort of a dance, okay? When you turn to the side, it pushes down. That's a result of your SAI. Now, when it pushes down, that means it's going to lift the fender. It's going to actually lift the body of the car up. The spring it's going to fight the spring. It's going to lift it. We don't, gravity wants to bring all things down. So when you get old and your muscles are weaker, you're going to start to slump. Okay. That's just a matter of fact. So if gravity's trying to push all things down and you do the turn and the spindle arc basically forces the body up, the body's like, I don't want to be up. I want to be down. So it's constantly trying to push back down, which is actually where we get our centering. The spindle arc gives us that steering return to center. And it was always kind of hard to explain, but I think showing you this makes the most sense. If you're turning, your spindle arc is down here, lifting the body up, and the body's trying to push back down, which automatically tries to recenter this. So if we had SAI that was messed up, that will affect the self-centering of the steering wheel. So I think it was yesterday, right? Nelly sent, or it might have been Monday, Nelly sent a video of a steering wheel. You'd kind of turn it, and next thing you know, the steering wheel would kind of run by itself and bump all the way into the steering stop. Now, you might not have caught that in the video, but I did because I've seen that before on customers' cars. So if you get a problem with your caster or your SAI, because they're kind of related, right? Caster is the steering axis. It's just from a different angle. If your steering axis is messed up, it'll make it so that it may not want to self-center anymore. If it doesn't want to self-center, you'll find you bump the steering wheel to the left and it's off to the races. It's like, heck yeah, I want to go left. Boom, and it'll go. But then it'll be harder to bring it back to the right. That could actually be a problem with the SAI. So for that car, I was thinking it could be, an issue with the electronic power steering or whatever. But then Nelly sent another picture of the car up in the air, and it looked like the suspension was pretty severely damaged. If you got damaged suspension, and the damaged suspension has messed with your SAI, that could cause a pull. It could cause poor steering wheel returnability. And let's pause right there. Poor steering wheel returnability, aka memory steer. That's where you may no longer get the spindle arc. If you don't have the spindle arc, you don't have necessarily the forces that try to recenter your steering wheel. So if you've got, let's say I'll be caster right here. Okay, if here's our caster and we've got the left caster way out and that's very positive, and our right caster is less positive, you see my hands, I'm already trying to steer to the right, right? It's similar with SAI. Everything that Caster does, SAI does. So what you learned about Caster, apply it to SAI. If you have insufficient Caster, you don't have good steering wheel returnability. If you have SAI that's messed up, you may not have good steering wheel returnability. Okay. If you have messed up Caster, you can have a pull. If you have messed up SAI, you could have a pull. We just don't typically measure SAI specifically. Okay. Additionally, yes, memory steer and poor returnability could also be caused by this upper strut mount bearing or that lower ball joint because they could be have a lot of friction and be stiff, right? So it's not to say that it's definitely SAI or Caster. It could also be the upper strut mount or the lower ball joint, or if we were to back it up, it could also be the upper ball joint or the lower ball joint if it's on a SLA or a double wishbone. Cool. And so again, if we're talking about the spindle arc, part of the reason that that happens is because the angle of the SAI, if you picture it's tilted in, that would mean it's kind of trying to steer the spindle up. And as you steer it, you can even visually see it, right? If I hold my arm dead straight and I turn, it does nothing. But see, if I tilt it in and I turn it, it does the arc. That's really the purpose of SAI. We're always going to have an SAI number that's going to give us some spindle arc. Cool. Okay, now we're going to add some things to this. So it's all about included angle, and included angle is appropriately named because it's SAI. See, there's your SAI, and your camber is included. Okay, so if your SAI was 10 degrees right here, right there is your 10 degrees, right? That doesn't include potentially what we've done with like oblong strut bolts right here on the McPherson strut. We might change those strut bolts to the smaller bolt or oblong, like some of what we saw in those aftermarket coilovers. We may oblong those and we may tweak just the wheel, which is really actually going to be the whole entire knuckle. But changing the knuckle isn't changing the SAI. The SAI is the strut mount to the lower ball joint. So if we slot those holes and move the knuckle, we're simply adjusting camber. Right. So we can adjust camber without messing up SAI. SAI should not be affected. So I'm going to define what SAI is. It's critical for the spindle arc, but if you are checking SAI, it's for diagnostic purposes. All right. You got a car that pulls, check the SAI. If your SAI is out of spec, anybody think they know what that means? Your SAI is out of spec. How did that happen? SAI out of spec because it was in a collision. Something's bent. That means something's damaged. Yeah, damaged. I just saw it on the chat. Good ones. So damaged components. Very good. So it's not something we do normally, but if there's an issue, like a pull, we check the SAI and the SAI is out. We're like, okay, this car's bent. Right. So now you're going to have to make a choice in your life. Are you going to be close enough? Or are you going to be like, not my problem, so I don't see it? Because ultimately what you should consider is getting your heart aligned to our job is to fix cars and we want to fix them well. And you may not get paid what you think you're worth, but most people don't. But if you have that front and center, eventually it will pay off. I'll bet you every dollar I got. Right now, I got a little bit of money in my pocket. I don't really care to give it up, so I'm not going to. I'm just going to tell you the truth and I'll be right. So you go ahead and you check SAI and you're like, oh, the SAI is off. That means there's something damaged. Are we done? Do we just ship it? What do you tell them? You tell them, hey, something's damaged. Have a nice day. And put yourself in the customer's shoes. They're going to say, okay, what do I do now? You're gonna say, I don't know, it's not my fault, it's not my problem. Close enough. Not my fault. And or you could say, well, take it to the body shop, because the body shop does have some ways to measure. That's actually the last thing I'm going to show you. The body shop can do some measurement that we don't traditionally do. They have different tools, they have different equipment. We have an alignment machine, they have a frame aligner. That machine is made to find bent parts and to tell you how much to pull. Okay. Um, or if you want to be, in my opinion, a better technician, you can be familiar with what the body shop does enough to look visually. If you look under, like this picture Nelly sent, that thing was what I would call schwankled. It's all bent up. You could totally see that control arm was bent. The ball joint was sitting at a crazy angle. Like that one's going to be fairly easy to find. The problem is it could be a bent control arm. It could be a bent strut. It could be a bent knuckle. It could be a number of things. So the problem is you don't, you, it's very hard to say exactly what is bent. And so the included angle is nothing more than a diagnostic angle. So we're going to do a little bit of math right now. If we've got 10 degrees of SAI, and then we've got a positive 1 degree of camber, what's 10 plus 1? Okay, if you didn't get 11, we got a problem. So 10 plus 1 is 11. That's the included angle. Now, this is what's crazy. You're like, well, who cares? Whatever. If you can look at SAI and the included angle and camber, you can get a really good idea of what's bent. All right. So, like in this case, 1 degree of camber plus 10 degrees of SAI is 11 degrees of included angle. Now, let's check out this one right here. We have -1 degree of camber, which that's kind of interesting. So same. This is intended to be the same vehicle, by the way. This is like before and this is after. So we had -1 degree of camber. We still have 10 degrees of SAI. And overall, the included angle is 9 degrees. So that's kind of interesting. If you were to look at that, it's almost like our included angle is too small. Our included angle should be larger. So the fact that our included angle is too little helps us to diagnose. If you look at this, doesn't it look like the wheel's bent in? No, it is. But is it bent in because the control arm got pulled out, or is it bent in maybe because the strut got bent inward? And you could punch this up in a chart and actually diagnose it. So I'm going to hold on that answer, and I'm actually gonna skip ahead. We didn't have the chart until up here, but let's just say this is for McPherson strut. Let's just say the SAI is correct, but the camber is less, and the included angle is less. Now, how would you know? You'd have to pull up the specs. You'd have to find out what is the spec for SAI, what is the spec for camber, what is the spec for included angle. If it was 10, the spec was 10 and the actual was 10, it's correct, right? What if the spec was 10 and the actual was less? Well, then we'd be down here at this one, okay? Or this one or this one. 3 possibilities. But it's correct, so we know it's either this one, bent spindle or strut, this one, bent spindle or strut, and that's the only possibilities. It's one of 2 correct. Now, it was correct. Does anybody remember what the camber was? The camber was either less or greater. It was -1, and it was supposed to be +1. So would you say that's less? I'd say that's less. Correct and less, and then your included angle was supposed to be 11, but it was actually only 9. So it was less. Would you agree? Less, correct, less, bent spindle and or strut. Okay, this is your diagnostic chart. Now let's back it up. Back the thing up right here. All right, our SAI was in spec, correct. Our camber was less. Our included angle was less. What was that supposed to be? A bent knuckle or strut? Take a look at this strut. Does this strut look funny to you? If you were to put a straight edge on there, I think you'd realize that strut's actually bent. All right, so knowing the included angle in the SAI and comparing it to the camber as well, that's going to help us perform the diagnosis. So a good tech would be like, all right, I don't do it often, but let me get my chart out and let me figure out what could be bent. It could be the knuckle or it could be the strut. And then at that point, you're looking very closely and you're going to say, well, I see that the strut is bent. So you got an option now. You say, well, you need a strut. The only thing is you're not totally sure if the knuckle's straight. So we could do this work, but it's not to say that we're the best people to do the work because the body shop can do better measurements than us. But the thing is, if you just tell the customer, I don't know, like I'm out, we don't know what to do, you're not really serving the customer well. Anybody in service should always be thinking of serving the customer. If you're an electrician and you cut open a wall and there's a leaking pipe, you don't just say, I don't know. You'd stop and you'd say, well, I'll fix your electrical, but you need to bring in a plumber. So if we're an automotive tech and we see a problem for collision, we at least need to advise the customer, hey, you're going to need to take this to a body shop and they're going to need to do a pull. But that's going to be expensive and inconvenient. So if we can use the chart to diagnose it, and even if you're going to sell them both the strut and the knuckle, because it's really hard to tell if a knuckle's bent, to be quite honest with you, hey, I still think that's pretty good service. I would say that's I would pass that. But if you were to say, I don't know, it's not my problem, this isn't what I do, just get it out of my sight, I'm not impressed with that. Cool. So we'll continue. We get to do a few more. This talks about as the SAI changes, that's going to have an effect on how the directional control is. So, like, you may have the vehicle handle different. This one, for example, doesn't have any SAI. That vehicle is not going to have good steering wheel returnability. So, this is again explaining more about SAI and how it can cause a pull. For example, like if you had one with small offset, this car is going to want to pull back to center. So if you turn to the left, this car is trying to recenter it, but this side isn't. So you're going to probably get more of a force and you're going to end up with a pull because there's unequal SAI. Makes sense? And so let's say that we're doing a little bit more diagnosis. Here we've got a vehicle. And let's say in some cases, changing camber will affect your, in all cases, changing camber affects your included angle, but it shouldn't affect your included angle in this case, because if you, or your SAI. If you look at this, take a look at your upper ball joint, your lower ball joint, right? If you were to go ahead and do your camber adjustment on this double wishbone, look at where that ball joint's going to go. Let's say this one has too much positive camber. You can see it, right? If you want to straighten out the positive camber, is it safe to say you want to stand this up? You can't adjust at your fingertips. There's no adjustment there. All you can adjust is at the elbow. So we've got to push the elbow out. And that's kind of what we're showing here. To adjust this, we would adjust at the control arm eccentric. You'd push the control arm outward, but look at what you're doing. Your upper control arm is fixed, and you just moved your lower control arm. So that is going to change your SAI, right? That's kind of what this is saying. Your SAI can change, and your true vertical will stay the same, and your camber can change. But if you change your camber right here, your SAI and your camber are going to move the same. Make sense? Because you're moving the lower ball joint, which controls your SAI and your camber. But the included angle should not change because you're moving them both together because the eccentric is at the base of the control arm. It's kind of crazy to think about, but in some suspensions, like for example, if we jump back to that McPherson strut, if you were to slot these bolts, you could change your camber, but it won't change your SAI. So if you look at this example, we slot those bolts, you're sliding your knuckle around, but your strut's not moving. It will change camber, but it won't affect SAI. It will change your included angle, though. It's kind of funny. The relationships are not real simple. Okay, so if it's on a double wishbone with the eccentric way inside, then your included angle should stay the same. Your SAI and your camber can change. As your SAI becomes more, your camber will become less. The total will be the same. This is not really crazy critical for you to fix the car, but it's just saying this is the reason we can use the chart. This is how the chart is made. The chart is made because when you change one thing, it has a predictable effect on the other. So when one goes up and the other should go down, if they both go up, we can kind of have an idea of what's bent, basically. So Renee, to answer your question, Kenny answered it. He's right. Depends on the system. All right, so now if we look at this one, when we do adjust that camber, as you can see, your SAI got much larger, right? But your camber got much smaller. And your included angle really should not change, right? It's 10-degree included angle, 10-degree included angle, even though our camber and SAI have changed. Cool, so it's just showing you there is a relationship. Now, on another one, if we adjust it, this is kind of review. I actually forgot that this slide was here. I thought I was so smart. I backed up, showed you one that I made up. So if it's a McPherson strut and your camber is adjusted at the knuckle, when you move the knuckle, that affects your camber, but it does not affect the strut and the control arm. So therefore, it doesn't affect your SAI. So it's kind of crazy if you change, if you slot the bolts and you start trying to change your camber, that camber angle is going to close up. Let's say you have camber of 1 degree. In this case, it's 2 degrees of camber. If you close that camber up to 1 degree, can't you see how it's going to close up your included angle? Your included angle was 10 degrees, and now your included angle is 8 degrees, 8.5 degrees, or 8 degrees and 30 minutes. All right, so once again, letting you know, depending on where you adjust your camber, it'll either move both of them, or either your included angle will change or it won't change. If it's at a eccentric at the base of the control arm, included angle is the same. But if it's at a knuckle with slotted bolts, your included angle will become will change, decrease if you're trying to decrease your camber. Okay, and then like this one, for example, here we've got the car before the accident. We've got 2 minutes and 2 degrees and 37 minutes of camber. I'm sorry, but in this case, we're looking at minutes, not just a decimal. You got 13 degrees and 4 minutes of SAI. Actually, I'm sorry, I forgot this one. This one on the right is the pre-accident. My fault. You got almost no camber, right? 37 minutes of camber. And your SAI is 13 degrees and 4 minutes. All right. And then your included angle is 12 degrees. I'll tell you what, let's drop the minutes. You got no camber, you got 13 degrees of SAI, you got 12 degrees of IA. That's normal. You get in an accident. Now you have -2 degrees of camber, 13 degrees of SAI, that's the same, but your included angle has changed. So SAI is normal, camber's less than it should be, included is normal. So plug that into the chart. And by the way, is this what type of suspension is this? Do you guys recall? McPherson strut. So we go over here. This is the McPherson strut table. This is the double wishbone table. They're two different tables. So we're on McPherson strut. Now, SAI. Do you guys remember what the SAI was? SAI is normal. Cool. So SAI being normal is either this one or this one. Now we didn't know, is camber less or greater? Okay. So camber, it was 0 and now it's -2. So is that less? So it's correct and less. And then we would presume that the included angle must be less or the same. Bent spindle or strut. Okay, so this is the chart in action. If you look at this, look, we followed the chart and we came up with a bent spindle, or in this case, I'd really consider that more a knuckle. All right, so just showing you the chart does work. Let's say it's let's say in this case a lower control arm. So this is normal over here. We've got SAI of 852. Our SAI later is what? It's not 852 anymore, it's less. So let's jump under there. SAI is less, okay? So it's less, less, less. The question is, what is camber? So we jump back. Camber was 0. Now the camber is positive. So the camber is more, would you say? So now SAI is less, but the camber is greater. So it's either, let me get my markers out here. It's either, where were we? We were at, I forgot where the heck we were. It was less and greater, right? Less and greater, less and greater. This is a no. So now we need to know, is the included angle correct? Or is the included angle greater? Anybody remember? Is the included angle less or greater? So it included angle was 852 and now it's 852. So isn't that the same? So it's correct. So which one's the answer? Right here. Right here. This became a no because it wasn't greater. So we've got bent control arm or strut tower out at the top. Let's put that to the test. Let me close my annotations. Oh, I want to delete my marks though. Well, I'm gonna have to delete my marks apparently later. Okay, look at that. The control arm is bent. So we got a bent lower control arm. That makes a lot of sense. Here we go. They're all the drawings. And to me, I'm visual. If I look, it looks like somebody slid it into the curb and the curb hit right here on the bottom and actually bent that control arm. So now you have a control arm that's essentially shorter. It was long, right? But as you bend something, it actually gets shorter. If you look at my hand at full length, let's say knuckles to elbow, it's an amount. But if I bend it, you see how now my knuckles and my elbow are closer together? That's because I hit it. I shortened it. So a shorter lower control arm would make that SAI, camber, and included angle have that relationship. So boom, we got it diagnosed. You may even look, if you can see the control arm's bent, you don't need to do this. If you look and you're like, oh, that control arm's bent, sometimes the paint chips and flakes off, it gets rusty. You can tell, no problem. But sometimes you're gonna look at it and you're gonna be like, I don't see anything. Everything looks fine. Well, that's when you'd go for some of these numbers, included angle, SAI, and camber, punch it into the chart, and then you'd be like, oh, well, it says it could be either, and remember there was two possibilities, a bent lower control arm or a strut tower out at the top. And the reason a strut tower out at the top makes sense is, look, you either bent the bottom in or you rip the top out. They'll both do the same thing. So which one is it? Well, you'd have to visualize it. If you look and that control arm looks good and you can kind of tell it had some crazy accident, we can replace a control arm. We can't pull a strut tower straight. Just the way it is. We could put a strut in, but we're more talking like the strut at the top bolts to the body of the car at the strut tower. We're talking about like the body of the car could be bent. I bet you it's going to be a lower control arm 9 out of 10 times. You slide it into the curb, this is what it does. This is actually what Nellie's picture looked like to me. It looked like they bonked it into the curb. They're probably out a little too many mucho cervezas and Cinco de Mayo and something. And next thing you know, I don't know, something like that. All right. So again, all the basically all the defects that can occur are on here. So if you have less, greater, correct, bent control arm. If you have less, greater, greater, bent control arm or strut tower out at the top and bent spindle or strut. So that one we were close at, it was correct. But if it were greater, that would tell us and a spindle. So pretty cool stuff. Very similar logic with was it $7,000 fix? I actually don't doubt that. Anytime a car is in an accident and suspension parts are bent, usually you want to call the insurance company. And it is what it is. So on the double wishbone, let's say we had SAI of less, camber of greater, included angle of correct, that would be a bent lower control arm. So you can see it's actually even more simple in the double wishbone style. So this is what you get when you have a car that has a problem though. See, you wouldn't just start jumping into this and being like, oh, let me check your included angle and your SAI and stuff. Like when I took the class, a lot of times they would focus so much on the technical. And then I go into the dealer and be like, yeah, I learned this in school. Check this and check that and check that. And they're kind of like, you're wasting time. And they were right. So a lot of times what the techs do is minimal because they want to do as many jobs as possible to flag the hours. And I get that. And on the jobs that don't need it, I'm blazing through it fast, super fast. But if I got a problem car, I may need to take the time to actually figure out what the heck is going on. I'll take my time on that car. So if I got an issue, I might do some of these measurements and really look into it. And I'll most likely be able to, figure the issue out. Additionally, when it talks about, some of those angles being changed, it does affect your scrub radius. So your scrub radius affects how difficult it is to turn the wheel, the vehicle stability, directional stability. So when you go around a turn and things like that, some of that has to do with scrub radius. A bent part will affect your scrub radius. So it can make it so a vehicle's unstable or, not handling as designed from the factory. Cool. And next. So there's some benefits of a scrub radius going to make it more stable. So again, scrub radius all has to do with where the steering axis intersects with true vertical, and having it a little bit above the ground is mostly from factory. When you start changing your wheels and tires, next thing you know, you're going to have, you're affecting your scrub radius. But you wouldn't affect it unequally side to side unless you bent something on one side. Okay, so now about turning angle. So this is the toe out on turns, and we did cover toe out on turns, but now that you've gotten some more time to do some of the work, I'm thinking that you'll understand this a little bit better. So let's say we've got a bent knuckle, because the knuckle can be bent in several ways, right? We can bend a strut, we can bend a control arm, but we can also bend a tie rod, which would be turning left to right, right? It's not all about up and down, in and out. It could be front to back, in and out too. So if we bend a control arm, or if we bend a tie rod end, our toe is going to be messed up. We can put a new tie rod end, or we could change the rack or the inner tie rod, whatever we do. We can fix that. But if it actually bends the steering arm, that's an integral part of the knuckle, we could do the alignment and we'll get them straight. But what you have to understand is the rate that it turns at will be incorrect. So normally we want the inner wheel to turn sharper and leave the outer wheel kind of lagging behind a little bit. Because if you look, we intersect those angles, they should all come together at this point. Cool. So if they were 30 degrees on the inner, we only want 28 degrees on the outer, and boom, those are going to come right to the perfect point, right in line with the rear axle. And that's when we got into that Ackermann geometry thing. Cool. That's how those steering arms, which are integrated in the knuckle, are designed, and they're the thing with the knuckle is they're forged or they're cast. Most of the time they're gonna be cast. So it's cast into a mold. Left knuckle, left knuckle, left knuckle. They'll just punch out a bunch of left knuckles, all having the same steering arm angle because they're mass produced. But let's say we bent the steering arm, yes, that would mess our toe up. But when we set the toe on the alignment machine, we'll be like, yeah, everything's cool. But then if you go around a turn and you notice one of the wheels kind of scrubbing, we'll say slipping, but I'd say scrubbing. That's when you're kind of chirpy, squawky, like that tire wants to go around this point, and your left tire wants around this point, and one of them is going to win and one of them is going to lose. They're not all trying to steer around one fixed location. So this one, in this case, is scrubbing across the ground. That's going to cause some weird tire wear. That's going to be kind of similar to toe wear, but it depending on exactly the details, it could tend to vary. But the customer is more likely to complain about like a squealing tire feeling weird. The way that we would measure that is you'd actually again have to go into the machine and tell it you want to measure toe out on turns. Sometimes you go in to one thing, it'll measure your included angle, your SAI, your toe out on turns, it'll measure all that, but it varies based on the software version. So if you want steering angle, or AKA toot, toe out on turns, you got to tell it you want that. And then you'll do it and it'll actually tell you the toe out on turn number or the turning angle. And if it's wrong, you know that it's the steering arm, which is integral part of the knuckle. So you could actually fix that for the customer as well. So kind of fun, a little more advanced. And this all has to do with the steering angle. So again, it's Ackermann geometry. The way that we have it work, we always want the outer wheel to have a little bit toe out, the way it is. Okay, now when we want to measure the steering arm, it can be a little bit tough. And as you're going to get into, it may give you, and this, by the way, is a little bit of a crappy picture. We're supposed to be looking down at the steering arm. All right, so they try, but it's hard to get it from the side. So if you're looking down, this is the steering arm's angle, and this angle should intersect with the rear wheels right at the dead center. Both of them should, but if it's messed up, we're going to have to try to measure that. You could try to measure like from the backing plate to the tie rod end, and the backing plate moves around, and there's just no real good way to measure it. Okay, so we're really going to measure it on the alignment machine using the toe out on turns function. Pretty much your only real option. And then setback we covered, but we'll touch up on it just a bit. You can see this car, they were going to park at Walmart, and they had one of those little islands where the trees are, and they didn't see it, and their front right tire smacked that curb, and they bent the something, I don't know, but they bent the right front wheel backwards. Now that changed the wheelbase. Let's say this was whatever, 12 feet from the factory. Now it's only 11 feet. It's actually set back, but we don't measure it in wheelbases because the alignment machine doesn't measure 12 feet and 11 feet. It actually measures this angle. So this angle is called the setback angle. It doesn't tell you the distance, it tells you the angle. If that's the case, we can do, some diagnosis. This is probably also going to mess up your caster. So if you have caster that's kind of negative or not positive enough, if you have insufficient, we may say, caster on the right front, and you have a setback angle of positive, you know that this tire got smacked rearward. That's a measurement. That's a function on the alignment machine as well. You can tell it you want to measure setback. We'll measure setback. Sometimes what I'll do just visually, I'll look at where the tire sits. I'll see how much of my hand I can fit between the tire and let's say like the fender near the driver's door and the passenger side door. I'll see like 4 fingers here, 3 there, or I'll get a tape measure. I'll measure it, and you can get a pretty good idea where the wheel's sitting. And usually I'm only doing that because, like what Edward showed and Mitchell were talking about, how they they did the lift kit on the Tacoma, the old man Emu, and he had the alignment done. The alignment tech, I think, did fine. And if there's no clearance, no issue because it's in spec. But if let's say that the customer did that lift and then they also wanted to do 33s on a Tacoma, you might be able to clear 33s without too much trouble. Let's say they want to do 35s. If you want to do 35s on a Tacoma, that tire is probably going to be hitting the frame right like on the cab. You'll want to set that wheel forward. I have cut them. You can cut the frame, plate it, hook it all up. It'll be sweet. But what I've also done before is set a bunch of positive caster. You set positive caster, you're doing kind of the opposite of this of what happened here. You're actually setting the wheel out forward. You can get it away from the frame. The only thing is then you're stuffing it up into the front bumper. But let's say that they got a custom front bumper, some ARB or something. If you got a bunch of room in the front bumper, move that sucker forward. I'll be doing that if I'm doing a custom alignment. Be like, yeah, it's the same. You know what I mean? I'll just kind of rough it in. But if you wanted to be precise, you could actually measure the setback. It's kind of fun. Some advanced stuff. Then if you had setback that was messed up, it could actually be something such as a bent frame. So let's say this one, for example, this is what we call a diamond frame where this took a pretty big hit right here and it actually bends this back. It tends to bend it back and it tends to pull it to the right as well. That would make it so your setback is unequal and you would actually be measuring that setback from the geometric center line to where we're actually intersecting both axles. So you'd like draw a line through both tires straight through, and they should be at a 90, but it's not at a 90, it's off. This would be a positive setback number. That's going to be an indication of something is bent. It's possible it could actually be the frame. Now, if you wanted to determine if it's the frame, that's probably about where we'll run out of gas. That's not really what we do. So it's coming though. It's coming. I'm going to show you. Now, as for bump steer, this also is another alignment, advanced alignment, but it's not so much the alignment as much as like how the vehicle handles. So if you go over a bump, let's say these guys are off-roading again. When you go over bumps, your steering wheel is doing some stuff. Like you could try to hold it really tight, but you don't really need to. As you're doing bump steer, if your suspension goes full compression, your tie rod is coming way up here. Your tie rod moved in, right? You can see that. If your tie rod moved in, that's going to make this steering, this pinion, because it's rack and pinion, it's going to make it turn. So your steering wheel is going to be doing some stuff. And that's all because of this visual of as you go over bumps, the tie rod doesn't get longer and shorter. It's going to want to, and as it kind of goes up, it may actually try to pull, and that's going to make the steering wheel turn. So just in case you want to know the source of the bump steer. Okay, and then here's where it gets technical. You have a car. You look at the chart, you know something's bent. You don't know if it's the frame, you don't know if it's the subframe, you don't know if it's a control arm, you don't know if it's the strut. This is where the body shop's work comes in. However, I want you to understand what the body shop does so that you know whether the car needs to go to the body shop or not. So like what Nelly said about that car that was banged up, they called the insurance company because as soon as you get into doing structural alignment and pulling and stuff, you need to call the insurance company. One of the videos I was going to show you was a guy pulling a frame. He just runs a frame machine. He charges $1,000 a day, but you got to bring the car in already stripped, all the panels off, all the parts off, bumper covers, and if the engine has to come out, it's all to be out. And then he's $1,000 a day to just do pull work. This is going to be expensive. There's just no cheap way to do it. The machines are expensive. You're using a top tier technician. They're expensive, rightfully so. So if we're looking at this right here, this is the repair manual. You actually have access to this in TIS, but it's not where we would normally go. You got to actually go under collision. And let's say this is a cross member, or they may call it a subframe. It'll tell you, well, from this little hole, let's say B, there's a hole right here. This hole to this hole, the left side is lowercase b and the right side is uppercase B, by the way. You should get 28.11. You're like, 28.11 what? And it's could be probably centimeters, because it's Japanese car. They could spec it in inches. They could spec it in millimeters. They could if it's 714 millimeters, that could be 28.11 inches. Or I really don't know exactly what the number is with this, because they didn't give us the key. They just cut this picture, but one of these is going to be centimeters, one can be inches. So from A to A, it should be, let's say, 30.59 inches. Do you have a tape measure that says 59 inch, 0.59? Does anybody have a tape measure that says 30.59? Tape measures don't work like that. This is not something where you're going to be to the quarter inch, the eighth inch, even the 16th, not even close. So we don't use tape measures on this work. We use what they call a Tram gauge or a tracking gauge. This is a much more precise tool. They didn't have real good pictures of it, but we're going to be actually looking for specs. And then a lot of times we're measuring side to side. And if it was crunched in, that number, let's say it's A to A should be 777. If it's 774, we know that it's bent, and we need to actually pull it with big hydraulic towers and chains till it's 777. We pull, measure, pull, measure, pull, measure. All right, 777, stop. But the thing is, it could be crunched in, but couldn't it also be twisted? So you'll notice a lot of times we also have a diagonal pull. So from little a to big A, that should be 791. And if it's twisted, that could be 797. And so you might actually have to pull it forward to get it to be that 791. So we're pulling in multiple directions. There's 2-dimension and another dimension. So it's a 3-dimensional pull. You can even be worried about the up and down. It gets a little tricky, right? And then you can see similar with, on frames with unibodies. And this kind of talks about a front, a center, and a rear when we're looking at collision work. And let's say that we're working on the center section. We should have 1,135 millimeters from E to F, but we should also have 936 from E to E. And that'll tell you if it's shortened this way or pulled this way. And most of the time, if it's in an accident, it's crunched up. It doesn't get stretched out. So if it's crunched this way and crunched this way, and then we pull it and we pull it, you're still not totally sure you're good, because you don't know if they're square. Okay. Those two rails need to be square. You guys know what I mean by square? I take 2 pencils. They need to be square. So these would be parallel. This would be square. So if they're parallel and you do a perfect 90, that'd be a perpendicular angle. That's square. If these are the right distance apart, but let's just say it's kind of, well, it's just not square. The best way to actually measure that is to pull a diagonal angle. So in math, does anybody remember Pythagorean theorem? I remember learning that. And I'm like, who cares? So stupid. What a waste of time. It kind of was. But I do appreciate the theory, because when I saw this, it made sense to me. A squared, B squared, C squared. So if you had 1135 and 912, you could actually calculate what this number should be if they're in fact at a right angle. How else are you going to measure this angle? You're going to try to put your protractor up there? You're not going to be able to measure that angle. So the way we measure that angle is we use Pythagorean theorem, A squared, B squared, C squared. Now the book's already done it for you. If you have 1135 and 912, and you were to punch those in as A squared and B squared, it would give you C squared should be, well, I don't know what C squared would be, but C would be 1,464 using Pythagorean theorem to make sure that they're actually squared up. Okay, so this is This is collision work. That's why there's a lot of front to back and side to side measurements, but then you'll see quite a bit of angled measurements as well, because that's how we tell if they're square, not just if they're straight. Kind of funny to think about. So it's a good thing to understand, but it's not exactly our work. So if you got a car and it's messed up and it's out of the league of what you can handle, that's why these cars get sent to the body shop, because this is what they do. This is structural prep. This isn't putting Bondo on and sanding it. Okay, this is like a little more heavy work. Cool. So here's like another example. And every car has something to reference. So sometimes it's the strut tower bolts, sometimes it's little holes in the radiator support, or there's all these different measurements. It can get kind of overwhelming. You imagine trying to do all these measurements in a car that was in an accident. You're not going to do it for cheap. If you can even know how to do it, you have to make good money doing this work to have it be precise, right? So there's your X measurement. Again, that's all about being square. It's very critical we have the strut towers in the right location. That's why we're referencing off so many things. We're measuring to B, which is the strut tower bolt, but we're measuring B to D, to the other B, to this F, to this E. We're making sure that thing's exactly where it's supposed to be, because that strut tower bolt or the nut, if there's probably 3 studs on the top of that mount, that's going to affect camber, caster, SAI. That's going to affect everything. It needs to be in the right spot. And if it's not in the right spot and you get the car, you're not going to be able to align it to spec. We've only got limited adjustment. If they get it really close, we can fine tune it. But on a lot of cars, there's no camber adjustment. So they pretty much need to have it right on the money. If it's still bent, or let's say it was bent and pulled, and they don't pull it to where it needs to be, you can't fix that. That's not what you're able to do. That car needs to go back to the frame machine. And unfortunately, by the time you find it, they probably have fenders on it, painted, all buttoned up. And you're going to be like, hey, this got to go back and be pulled. And they'll be like, what the heck? Because I'll show you what it looks like when you're going to pull a car. All right, here's the first thing. This one's pretty good. Should be able to pull this up. Whatever. Oh, you better stop it. Okay, let me see if it's interesting. I tested this out on my computer and it was fine, but apparently this one said no. Oh yeah, I totally made it mad. All right, no problem. I'm gonna pull that link. Let me see. Open link. Yeah, here we go. Okay, so this is showing you those tools. What he's using is a tram gauge.
Welcome to this video on mechanical gauging and measuring. We're going to discuss how to use mechanical tram gauges and self-centering gauges to measure all 3 dimensions on a vehicle body. That's right, all 3 dimensions. It's a common misconception that you cannot measure 3 dimensions mechanically, but that's not true. As you can see with the equipment on this board, we can measure all 3 dimensions on a body, very similar to how this electronic system here would measure all 3 dimensions on a vehicle body. Let's start off by reviewing the measurements for this vehicle. We are going to have a look at the upper body measurements as seen here, which shows us underhood and all the openings. Those are all point to point. This next diagram is of the underbody, which shows us on the upper half point to point measurements, and on the lower half all of the parallel to dated measurements. We'll discuss a little bit later on how to utilize those 2 halves of the sheet. And on the right side, we'll see all the measuring points corresponding to a letter for each of those sections. This is what the computer screen would look like as we select these areas to print, if you choose to print them. The alternative is to actually record all of your measurements in the software. That way you can record all of the preliminary measurements beforehand, and then record the measurements after you've done the corrections to the vehicle. And that's a great way for record keeping professionally all of the work that you've done on the vehicle. Here we have 2 mechanical tram gauges. The one in the green box is a conventional mechanical tram gauge. The one in the red box is a digital tram gauge. The difference is the digital tram gauge will give a digital measuring for the readout of the length. However, there are some limitations. That does, however, create some convenience during the measuring process. When using a tram gauge to measure point to point, make sure that the pointers on each end of the tram gauge are equal in length. This is important or else your measurement will be off. So here we are measuring the lengths with a measuring tape to ensure accuracy. Once we have the length of the pointer set, then we can set the tram gauge to the correct dimension for the vehicle. So I'm measuring with a measuring tape from the outside of one pointer to the inside of the next pointer. We can also go inside to outside. This is necessary to compensate for the width of the pointer. You could measure from the point to the point, but it is much more difficult. Notice how the pointer sits on the center of the stud. If you're measuring a hole, make sure that the pointer sits centered in the hole and is not too big as seen here. If the pointer is too big for the holes, we can put an end on the pointer to prevent it from going into the hole. However, if we are using these ends, we have to make sure that both pointers on the tram gauge use the same part, or else we could make the measurement off because it does change the length of the pointer ends. Here I am doing a point-to-point measurement under hood on this vehicle. I am making sure that the pointers are centered on the bolt heads. I've also ensured previously that those ends are equal length. I have not, however, preset the length or width, if you prefer, of the actual tram gauge. The reason I did that is so I can measure this particular length rather than compare it to the actual length that it's supposed to be. So what I've done now is lock the tram gauge into the dimension I measured. I'm now double checking with the measuring tape towards the ends of the pointers to ensure accuracy. And then I will record that measurement and compare it to what the measurement is supposed to be on the vehicle.
So do you guys notice the tram gauge doesn't do the measurement in this case? You basically set the tram gauge up and you lock it in place and then you move it and then you measure it. Okay, so that's one point I just wanted to, that this is what he's doing right here is old school. It gets a little more high tech.
Vehicle, I have a tolerance of plus or minus 3 millimeters. You'll notice that I measured 1,310 millimeters as compared to the 1,308. That means this dimension is 2 millimeters longer, but still within that plus or minus 3 millimeter spec. Body opening measurements are noted here, and we can see that there are letters designating the measuring points. They are showing notches in this case on the body, and I found the notches here in the opening. Then I'm going to take the tram gauge and put the tram gauge into these notches that I found on the body. Sometimes these can be rather vague or difficult to find points. So I'm going to take the tram gauge and place it in these 2 points and measure my opening. This can be particularly useful if the vehicle is in a side hip. You may or may not want to preset the tram gauge depending on your preference. Moving on to the underbody, we need to find the body's 0 points, which are designated by these triangles. So here we can see the letters K and N representing those body's 0 points, which have been highlighted in blue. Now, why do we want to note those? We want to note those because those are the areas that we want to measure first, which help us to measure the center section, if you remember the principle of separating the vehicle into front, center, and rear sections. Using the legend on the chart, I was able to locate these holes. Some software will tell us where these holes are by showing us pictures, or they'll show us pictures of any other measuring points too, which can be handy. I've removed the plugs from these holes. However, this last plug in the right rear corner is a little bit challenging as I have not removed the plug yet. I will need to reposition the arm for the hoist to do this particular spot. I've highlighted that center section here. Again, the center section is critical and should always be the first area we measure. And we should always do point-to-point measurements before we start measuring for height from the data. Have a look here. I've recorded all the measurements that we did point to point. You'll see that most of these measurements are within the plus or minus 3 millimeter specification. You can record your measurements on the sheet as I have done, or on the side, the back, or another piece of paper. Or, as I mentioned earlier in the video, you could also record them in the software. So in this particular case, since we're using Mitchell, we do have that ability. Longer point-to-point measurements can be challenging, so here I'm asking Rob if he'll come over and give me a hand. So Rob is going to give me a hand holding this tram gauge. As I do those long measurements, the tram gauge can be very hard to hold, and it can be almost impossible to tell if both ends are centered properly in the holes or on the bolt heads. So here we are setting them in the holes, and then I'm tightening the gauge so that I can remove it and then measure with the measuring tape to determine the actual length of this dimension. Adding a third pointer to the tram gauge turns it into a trammel or tracking gauge, which allows us to measure two dimensions. Those would be height and length, or height and width. And what that does is allows us to measure those two dimensions simultaneously, whereas a typical two-pointer tram gauge only measures length or width. Here we are placing the gauge on the vehicle. If the pointers fit in the holes, then we are good. If not, then we will have a visual indication of any height misalignment and or length or width misalignment on the vehicle. We can then measure and record those dimensions on our sheet. As we transition into parallel data measurements, this is a good time to note to check your equipment for damage as seen here. Those will give you false readings. The ends of the self-centering gauges need to be hung from the points you're measuring from. So if this is the hole we're measuring from, that roll pin could fit nicely into that hole to hold the gauge. There is another end with a smaller roll pin that can slide onto the opposite end of that piece, which has a hole in it. So we pull this pin out and slide it into the end, as you can see here. And then that smaller roll pin will fit into the hole or other place that you're trying to hang the gauge from. The small roll pin is great for fitting into small holes. Just make sure it fits tight to the end or edge of the hole. We have several other ends that can fit into this area as well. So we're going to remove this particular one, and then we're going to slide another end on that can also hang out of holes. This one's very common and works very well for most average size holes underneath the vehicle. Put this one in the hole, and it should hold the gauge in place. As you can see, it can work in small holes or large holes. We will remove this particular end, and we have another end we can put on here as well that can work in some circumstances. So this other end we're putting on is a magnet. This magnet can fit on a bolt head or anywhere that's magnetic underneath the vehicle. Make sure the magnetic end is strong enough, otherwise it could fall off the vehicle. I generally do not recommend using these ends unless you absolutely have to use those particular spots. The next end that we have on here is another one that may not be used very often, and that has this pin on the end. This pin can actually go outside the rocker panel and fit between the door and the rocker, holding the gauge in place. One thing to note with this particular centering gauge is the centering gauge does not actually have to be hung from the hole that you're measuring from. It just has to be hung on areas that are symmetrical on both sides of the body and stable, so long as when we hang it, we're measuring from the correct measuring point. You can hang it from anywhere symmetrical, but must measure from your correct measuring point. We always have to measure from the correct measuring point, be it a hole, bolt, or something else, regardless of how the gauge is hung. In this case, we're measuring from a hole. One end of the measuring tape is on the edge of the hole. The other end of the measuring tape, as you can see with the red arrow, is pointing to a particular spot on the centering gauge. It doesn't matter where in the centering gauge we measure to, as long as it's a fixed point and that all of the measurements are taken to the same spot on the gauges. You could measure to the yellow or orange bar, top or bottom, provided that you're doing the same thing on all bars. If you do not do that, and you're not consistent, you will have inaccurate datum measurements. To use the centering gauges, we're going to refer to the parallel to datum measurements. I am referencing the point-to-point up top, though, because I want to set the first two gauges at those body 0 points. My datum will not clear the vehicle, so I'm going to add 100 millimeters to each point manually. So as you can see here, I've taken the measurement, 166 millimeters, added 100 to get 266. To prepare the centering.
All right, and you guys kind of get the idea. Let's skip the rest. Basically, this is collision work. This is what they do. They're measuring point to point on a lot of these. They do in some cases use the digital type, which gives you the straight up number. Seems to me like that would save a lot of time. But do you think we have what it takes to do this work in the dealership? It's not what we do. You should at least understand it, though. If it did have a damage or some sort of an issue, we should at least be able to identify it, and then we should be able to send them to the correct type of a facility. Now let me see. Oh, I see what it's doing. It's trying to open these
Drinking
in
warm water before bed balances
Ed.
blood sugar levels and reverses type 2. Thousands of people are.
So now I'm going to show you something that's a little more similar to us. How they were doing that, sort of how we used to do alignments, but ours were just much easier. We were doing something like a tram gauge, but we do it with like a string or a tape measure because we didn't have to be that exact. We do the front of the tire and the rear of the tire. That would tell us our total toe. We could use bubbles and the plumb line and stuff to measure our camber. No different than like us. We got an alignment machine that uses laser measuring. That's all that you guys know. That's for the most part, that's really all that I know. I understand some of the basic theories, but I did not have to align cars with the shoestring. But collision work has gone laser as well. Here's one. This one's short from SEMA. You'll be shocked at how this one works. Oops, I already had it full screen.
Hi, I'm Richard Perry with Chief Collision Technologies here at SEMA, and we're going to talk about our Meridian measuring system. This is our three-dimensional laser measuring system. Allows us to measure multiple points throughout the vehicle, identifying any structural misalignment, and also identifying the direction we need to pull during that repair process. With this, we've got a single hub measuring system. This allows us to measure 360 degrees, identifying any target in line of sight. We've got continuous measuring on every target that's being measured on the vehicle. So it's going to constantly give us an update and allows us to identify if we're headed in the right direction during the repair process and when we finally get to the correct position according to the OEM specification.
All right, hold on right there. Check that out for a quick second. So they've got the center hub level shooting lasers, and you see all these, like this number 15 Chief and all these are in those points that they were using the tram gauge on, going point to point, point to point, point to point. They've got several of those centering points. Boom, boom, boom. You put these in place, and then you turn the level on, and it'll actually measure the distance of all of them in 3 dimensions right off the bat. You guys can see how much more efficient and time that's going to be and how it's pretty amazing. But what he's also saying is you could keep this measuring live while you're doing the pull. If you're pulling, you're watching the number change live. You don't have to stop the pull, measure, pull some more, measure, pull some more, measure. You're pulling and you're watching it increase, increase, increase until you get to the number. Then boom, you've got your pull. Now, to be quite honest with you, I'm not the expert to really teach this. I know enough to be able to translate it so you can understand it. If you really wanted to pursue this, it's a different craft. They do different work than us. We don't do the same type of work. Now we'll finish this one out. We'll look at a couple quick things. We'll see how much it costs.
When we finally get to the correct position according to the OEM specification. Come see us here at SEMA, and when you do, have yourself a chance to win a Meridian here. We're giving away a first prize of a Meridian, second prize of a 522 welder, and then third prize is a rivet gun. So come take a chance, sign up, come see us.
So when you guys go to SEMA, these are some of the things that I would check out if it was up to me. If we were to look up frame, pull, machine, I didn't get a video on this one, but if we were to look at just I'm sorry, I'm going to Google. I don't know how to use this Edge business. So if I were to just look at frame puller, look at images, and if you look at something like this one's for sale pretty cheap. You pull the car up on here, you'd actually bolt it down. It physically clamps the pinch welds, holds it down to this machine. And then if you look, each of these are the towers. You could actually angle this and get it in the right position and then attach that chain to a point you want to pull using various different attachments. And then hydraulically, it's going to pull this chain down or up. In this case, it's actually the chain would be held here and this tower is going to expand. And based on this pulley system, it's going to pull it outward. So you could angle this in the direction you think it needs to go, and you'd be operating the pedal, and it would just literally be stretching the metal out. But how far do you stretch it? Well, you got to stretch it till it's within spec. So in the older school, they'd be measuring and tramming. In the newer school, you'd have that level system hooked up, and you'd be watching the screen and pulling until it gets in the green, kind of like what we do. It's very similar. The improvements are very similar to our alignment equipment improvements. Now, if we were to just check Google for, let's say that Chief Meridian, this is just the measuring system. I don't know if I can get the price for the measuring system. Yeah, it doesn't look like I'll be able to get that price. It's not going to be cheap, and that's just the measuring system. Now, I'm not going to say it's not worth it because you see how much time that's saved, but I can't even apparently get you a price on that. I might jump on eBay just because that's where we found that machine. Yeah, so 30 grand, and I bet you it's probably more retail just to do the measuring. Now, if you wanted to do a Chief frame aligner, you're looking that, see, this is old. We got some alignment machines that look like that, but you've got Chief frame. Let's see, or I might just do even just frame aligner. And then let's do, you can see it's going to get all the kind of junk. If we were to go, yeah, that's frame pull. Let's just do frame machine. Okay, 10 grand for a Chinese one. It's realistically, it's going to be more. So they're spending pretty big bucks to be able to have a frame machine and the alignment machine and the aligner measuring system and all that. It's just way different work than what we do. So hopefully you guys kind of learned a little something about advanced angles. We can do what we do. If they can pull the frame 95% of the way there, we can probably dial in the wheel alignment in just a little bit. But if you can't get it into spec, it's probably because it needs to really be pulled. It needs to be measured and trammed and all that stuff. Okay. So that is everything I got.